Okay. So now we raised the other important class of non-linear recombination called the Auger recombination. Auger recombination is a free carrier process. It must include an electron and a hole. And while the electron and the hole recombine, the energy is transferred to either the third electron or the third hole. So no photon comes out. The energy is just consumed. For example, for this case, with the energy transferred to third electron, the electron is excited to a higher band. Then it eventually goes back down with the energy transferred to the whole lattice, and it becomes the lattice vibration. So it is non-linear. So obviously, this will happen, or which will be important when the injection carrier density is high. If the carrier density is very low, then it's very unlikely to find another carrier to capture this energy. Yeah, so it happens only when the carrier density is more significant when the carrier density is high. And according to the mechanism, we can further net it with 4 later because there will be 4 states. For example, for this one, it is electron 1 combined with the hole number 3. And the energy transferred to the electron number 2 is excited to the level number 4. So it will include the 4 states. And we can call it from the high to low. For example, the CCCH process is the conduction band, heavy hole. Okay. And this is CHHS process. What does happen here? An electron recombine with a hole in the heavy hole band, and the energy is transferred to another hole here, which excites an electron in the speed of hole band, goes up to the heavy hole. Okay. So it is conduction band, heavy hole, speed of hole. From high to low, so it is the CHHS process. Similarly, CHHL, the L is the dipole band. And such recombination need to satisfy the fundamental conservation of physical parameter. One is the conservation of energy. Second is the conservation of momentum. So let's consider the K represents its momentum and the E represents its energy. Because the conservation of momentum is originally 2 electrons at the number 1 and the number 2. For most of the case, number 1 is equal to number 2. Yeah, because if the momentum is quite different, the energy exchange will be rather difficult. So although it's not necessary to be equal, but usually we can just regard it K1 is equal to K2. Anyway, so in the beginning it is K1 and K2. After Auger recombination, it becomes K3 and K4. So due to the conservation of momentum, it should be K4 plus K3 should be K1 plus K2. And usually the same is equal to K0. Okay, so this is the conservation of momentum. Second, the energy is conserved. So the energy of these 2 electrons should be the energy of these 2 electrons. So that will be E4. E4 means the energy for here. Minus E0. So the level here is 0. So this means the energy absorbed, E4 minus 2E0, should be equal to E0 minus E3. Okay, so what does that mean? You can imagine the Auger recombination is trying to find a plot like this. Two identical triangles. While this length is equal to this length, and this length is equal to this length. These two lengths is for conservation of momentum, and this is for the conservation of energy. And if you can find this pattern on your band structure with file this 3 point matches this band structure, then the Auger recombination could happen. Alright. So with some mathematical work, a mathematical work is here. I cannot skip that. If you're interested, you will see how this comes out. After some mathematical work, because the boundary condition that you need to find a 3 point satisfy this relation. The number of K0 cannot be too small. It cannot be at the event edge. It has a minimal value. That the E4, and how high the E4 is. The E4 must be larger than this value. This value, this 2mc means this is the effective mass of the conduction band or the electron. mh is the effective mass of the heavy hole, and divided by mc plus mh. And the E0 is also equal to this number times band gap. So for a conduction band like this, the electron near the band edge will not undergo Auger recombination because it is impossible to find any other point in the heavy hole satisfy both energy conservation and momentum conservation. It needs to start with something like this, the E0. And the E0, let me know, delta E0 is the difference between EC. So this is EC. E0 minus EC should be some constant times its band gap. So what does that mean? Okay, so how does this comes out? It's already in this page. Yeah. But I'm not going to repeat that. It's pure mathematical. I said it's a very exciting mathematical work. I will leave it to double check with that. Okay, so let's take in the CCCH project. Think this will happen only when first there are electrons occupied at the energy 0. Second, the whole electron is not occupied at energy 4. Third, the electron is not occupied at energy 3. But if there is no hole, for example, if there is no field, the electron has nowhere to go, so this process is not going to happen. Okay, so you need this level to be occupied, and the end level to be vacant. So this recombination rate should be proportional to F1 squared times 1 minus F4 times 1 minus F3 Okay, so if for most of case, if the band gap is large, then that means the level of minimum F4 will be higher. When the energy of 4 is high, F4 is almost 0. So that doesn't have a strong influence. 1 minus S4 is usually very close to 0. So it's not an important factor. The important factor is this 1 minus F3. We said that the delta E3. Delta E3 means the it's different to the band edge. Because the E3 must to be some constant, since they are all effective the division between effective mass, the more important is its band gap. If the material has a wide band gap, a wide band gap means the minimal recombination of Auger recombination need go to deeper. Then we need a hole in a deeper place, which makes the population factor unlikely. Because while the E3 is deep, F3 will approach to 1. So the Auger recombination will be unlikely. So wide band gap materials suffer much less than narrow band gap materials for the Auger recombination. Okay, so this is the similar and I just already used the result. So for the CHHS process, the delta E4 also has a minimal process. Yeah. So the energy flow could not be less than such value. Okay. With the old marks you need that. So the basically the derivation procedure is the same with this page. If you can understand this page, maybe you can try to derive these two equations. And if you can show me because there's no homework for this one, so this will be the additional homework for the homework number 3. Yeah, you can just mail to me, show me your progress, and if it works, I think your progress is correct, then you can directly get 1 point in the final progress. Okay, so we said that we only take the CSH for example. Because the 1 minus F4 is not important, because the F4 is at a really high level. So the 1 minus F4 is actually very close to 1, so it's not a problem. So it should be more proportional to F1 squared times 1 minus F3 only. And the F1 is relevant to its electron density. 1 minus F3 is relevant to its hole density. So for the CHHH progress, the radiate recombination rate should be proportional to its N squared P. So it's a third order relationship to the carrier density. Since it has CCCH, similar thing can happen with the heavy hole, light hole, or speedo hole. So we just combine them all together. Call it CNN squared P. And similarly, we can do all the potential combinations anyway. For empirically, we will just further assume the N should be equal to P, or the charge neutral T, 电中式. Then the whole process becomes a constant times the carrier density cubic. So it's could be also writing as the Auger recombination current divided by Q. Yeah, when the current divided by Q means the number of electrons. Then divided by V, it's volume. This is high voltage, is the active volume. So it becomes the recombination density. Okay. So the whole carrier recombination procedure could be written in three terms. One is the Shapley reform. We call it AN. Second is the BN squared. It's the spontaneous emission. Things we haven't taken into the cavity and the stimulation into account. Third is the Auger recombination for CM cubic. So this is called the ABC model of the carrier recombination. Or we can just see it as a polynomial fitting. But every polynomial fitting has its physical significance. Then the radiated efficiency can be defined as the denominator is the total recombination rate. It could be Shapley reform, spontaneous emission. Yeah, spontaneous emission and the Auger recombination. But only those with spontaneous count because it is the radiated efficiency. Then it's written down something like this: Bn squared divided by An plus Bn squared plus Cn cubic. Then we can do a simple calculation to make a differentiation of delta R to N. We will see that the IQE is a function of carrier concentration. And it will have an optimal value. The efficiency of an arbitrary device usually looks like this. So when the carrier density or when the current, injection current, is really low, it is dominated by Shapley recombination. If the carrier density is really high, it is dominated by the Auger recombination. It only happens when the carrier's density is in the middle, then you might get the best efficiency of the LED devices. Now I need to be clear. Since now we only care about LED efficiency because we haven't to set the term of stimulated emission inside. Yeah. Alright. Okay, so let's see the material dependent constant of the Auger recombination. For INGAST, the band gap which is only 0.8 eV, which corresponding to the communication laser, 1.55 micron laser. The C is around in the E minus 29. For the unit is centimeters power 6 times inverse second. Okay. Currently, for those with a small band gap, usually has a severe Auger recombination. For the material with a wider band gap, you see the coefficient, Auger coefficient is much less. For this one, it's only 2 orders smaller. Oh, this is also from the reference. However, this process can also be assisted by the Phonon. So what we said here is doesn't consist any phonon. So you need to fulfill the conservation of momentum by themselves. So it will be rather difficult. But if you include the phonon, yeah, the conservation of if there is no phonon, the progress should be like this. One is here, and okay. So electron, hole, vacant state, something like this. However, if we have phonon included, you can have it like this. We need to change another. Okay, probably we can one with here, and the one is okay. Infinitely far because you cannot take your state. But with some assistance of phonon, yeah, you can still make a conservation of the momentum. But this progress is also unlikely because you need to find an electron to meet a phonon at the same place and at the same time. So it's just like the case of the red band gap and non-direct band gap. The phonon assisted Auger recombination is actually unlikely compared to the direct Auger recombination. However, if the band gap is so large, it's rather large, the direct Auger recombination also become unlikely. That will make the importance of the indirect band gap material also important. So probably 50%. So it's a long story that the people are arguing whether the Auger recombination exists in nitride material. If we just take the classical and classical theory appeared here, a material with a 4.4 eV should have no Auger recombination because the C, according to some theoretical calculation, is in the level of E minus 36, so practically impossible. But we still measure devices with a grading efficiency as the carrier density goes up. What does happen? So that becomes a very strong argument over 5 years. Yeah, from that's why I'm starting my PhD.